I would like to go over one example from the book. This is exercise 2.7.4, and this is an example of testing whether or not a transformed frame of reference is a canonical transformation. Okay. So I've given right here the question, and so we can see that we want to verify that in this rotated frame, so we're rotating from x and y with components and momentum px, py, and we want to see if we rotate it into the x bar, y bar frame of reference. So they gave us the transformed equations for these variables, and we want to test and see whether or not it's a canonical transformation. Okay. So basically, I'll rewrite the equations, or basically, I'll start. We'll write down the conditions. The conditions we need to prove that it's a canonical transformation here. So the conditions that we're going to test are the two coordinates, and those should be equal to 0. We can test the momentum components, and the Poisson bracket for those should also be equal to 0. And if we test the position with the momentum component of the position, that should be 1, because that's a Kronecker delta. The position in y, the Poisson bracket with the y component of the momentum should be equal to 1. And then we should also see that the x component, the Poisson bracket of the x component and the x coordinate and the y component of the momentum, sorry, getting a little sloppy here. The y component of the momentum should be equal to 0, just like the Poisson bracket of the y coordinate with the x component of the momentum should also be 0. So basically what I want to do is I want to work out these 6 Poisson brackets to prove that this is a canonical transformation. So let's start with the first one. The Poisson bracket of x bar, y bar is equal to the derivative of x bar with respect to x, the derivative of y bar with respect to px, minus the derivative of x bar with respect to px, and the derivative of y bar with respect to x. That's the first one in the sum, but remember there's two coordinates. There's the x coordinate and the y coordinate. So now I have to work out the derivative of x bar with respect to y, the derivative of y bar with respect to py, minus the derivative of x bar with respect to py, and the derivative of y bar with respect to y. So that's where, remember the definition of the Poisson bracket, there's a summation over all coordinates, and so we've had to now take the derivatives with respect to x and px and y and py. Okay, so let's do that. So here are our equations, and so the derivative of x bar with respect to x, if we look at the first equation on the assignment, that gives us a cosine theta. The derivative of y bar with respect to px, y bar doesn't have any px in it, so that's 0. The derivative of x bar with respect to px is also 0. There's no px variable in the x bar equation. And then derivative of y bar with respect to x is sine of theta. Okay. The derivative of x bar with respect to y is minus sine of theta. The derivative of y bar with respect to py is 0. And now the derivative of x bar with respect to py is 0, and the derivative of y bar with respect to y is cosine. So we've worked out all 8 of those derivatives, and now we put that into the equation right up here. And when I do that, I get the Poisson bracket of cosine of theta times 0 minus 0 times the sine of theta plus the minus sine theta times 0 minus 0 times cosine theta. So there's a 0 multiplied by every single term, and so sure enough, the Poisson bracket of x and y is 0. So that first Poisson bracket works out to be 0. Now we can work out the Poisson bracket for the momentum. And we have px bar, derivative of px with respect to x, the derivative of py with respect to px, minus the derivative of px bar with respect to px, and the derivative of py bar with respect to x, plus the derivative of px bar with respect to y, derivative of py bar with respect to py, minus the derivative of px bar with respect to py, and the derivative of py bar with respect to y. Okay, so looking through the equations, we can kind of see by inspection that any of the derivatives which have a derivative of the momentum with respect to x or y is going to be 0. So this term is 0, this term is 0, this term is going to be equal to 0, and this term is going to equal to 0. So in this case, the Poisson bracket turns out to be 0. So far we're 2 for 2. Now let's check out the Poisson bracket for x bar and py bar. And we have the derivative of x bar with respect to x, the derivative of p bar y with respect to px, minus the derivative of x bar with respect to px, the derivative of py bar with respect to x, plus the derivative of x bar with respect to y, the derivative of py bar with respect to py, minus the derivative of x bar with respect to py, and the derivative of py bar with respect to y. So we've gone through all of the different the both dimensions x and y, and now if I look through it, what do I get? I get the derivative of x bar with respect to x is cosine theta. Derivative of py bar with respect to px is sine theta, minus 0 times 0, plus minus the sine of theta times the cosine of theta minus 0 times 0. So I'm quickly going through those derivatives, and while we do have terms that are non-zero, it turns out they're exactly the same. And they're equal to 0. So that Poisson bracket of an x coordinate and a y component of the momentum gives you 0, like we said it was. Okay, so now let's try the complement And what's the Poisson bracket of the y coordinate with px? And let's write them all out. Derivative of y bar with respect to x, derivative of px bar with respect to px, minus derivative of y bar with respect to px, derivative of px bar with respect to x, plus dy bar dy, dpx bar dpy, minus py bar, derivative of y bar with respect to py, derivative of px bar with respect to y. Oof. Okay. Okay, so let's add in those derivatives. So what do we get? We get sine theta sine of theta times cosine of theta minus 0 times 0 plus cosine of theta times minus the sine of theta minus 0 times 0. So again, we have non-zero terms, but they turn out to be exactly the same, and when we subtract them, we get 0. So we've gone through the 4 combinations of Poisson brackets of coordinate with coordinate, and Poisson bracket with the coordinate with the opposite component of the momentum, and all those 4 turn out to be 0. So the last 2 Poisson brackets, we work through them, they should give us a 1. So the Poisson bracket of the x component with the, the x coordinate with the x component of the momentum is the derivative of x bar with respect to x, derivative of p bar x with respect to px, minus derivative of px with respect to px bar, with respect to px, derivative of px bar with respect to x, okay, plus the derivative of x bar with respect to y, derivative of px bar with respect to py, minus the derivative of x bar with respect to py, derivative of px bar with respect to y. So we have all of the things are worked out now, and if we go through the derivatives, we get cosine theta times cosine theta minus 0 times 0 plus negative sine theta times negative sine theta minus 0 times 0, and that's cosine squared theta plus sine squared theta, and everybody should know that trig identity is 1. So sure enough, the Poisson bracket of x bar px bar is the result of the Kronecker delta of 1. Okay. So I could also now work out the Poisson bracket for y bar py bar. We could work that one out. And if we did, what we would end up finding is 1. So I'm not going to actually go through the last, the 6th Poisson bracket, but instead, you've seen the pattern there, and we've gone through explicitly each of those derivatives, and all of these Poisson brackets confirm that this transformation, this rotation from x and y, px, py, to x bar, y bar, px bar, py bar, is a canonical transformation.